Disseminate, the Computer Science Research Podcast.
Hey everyone, welcome to Disseminate, the Computer Science Research Podcast. I'm your host, Jack Waudby. This is the first episode of 2026, so a very belated Happy New Year to all of you computer science research enthusiasts out there. In today's show, we are going to be talking about a paper that was published at VLDB last year that actually won the Best Research Paper Award, and that is AnyBlox, a framework for self-decoding datasets. And I'm really pleased to say I've got one of the authors of that paper with me today, Mateusz Gienieczko. So welcome, Matt.
Hello.
Cool. So we always start off as customary on the podcast with you telling the listeners a little bit about your journey and how you kind of arrived at where you are today. And I did do a little bit of research, and I know that you wrote your first line of code in 2013. And to quote from your homepage, this made a lot of people very angry, and it's been widely regarded as a bad move. So yeah, maybe take us through your story, Matt.
Yeah. I just started coding in high school. That was around that time. I did my bachelor's and master's in Warsaw in computer science. My master's thesis was RSonPath, which is the blazing fast JSON path engine. It was published in ASPOS 23. The title of the paper is Supporting Descendants in SIMD Accelerated JSON Path. It was a fun project with an intersection of like some theory of automata, which always fascinated me, like computation theory, and low-level tinkering, because SIMD you have to use low-level code, which I didn't do much before. I had industry experience as well, mostly doing .NET, like backend development, cloud stuff, talking to databases, but not writing databases. I went to work at Microsoft for a year in Dublin, identity. It was not fun. And I started looking for a PhD because I reckoned that I should try with an academic career before like the industry sucks out the rest of my soul. And I had the opportunity to work at TU under. Well, it's complicated actually. Like our labs are pretty intertwined between Professor Neumann, Professor Gicheva, and Professor Leis. But now I'm supervised by Professor Jana Gicheva at the database chair and data processing. So that's what I do. And AnyBlox was my first paper. So now I'm. Jesus, I was 2 years already of the PhD. This is my third year.
Time flies, man. Yeah, time goes quick. You'll soon be graduated.
That's scary.
Yeah, but I guess the plan is long term
yeah.
then to stay in academia, right? And that's the career you'd like to pursue. Industry wasn't for you.
That's how I feel right now. It of course might change. The landscape and like the job market evolves so quickly nowadays that it's really hard to make long-term plans. But I feel much better doing what I'm doing now than I did at any company that I worked at. So this is much more exciting.
Fantastic. Yeah, well, I see your research career definitely has started strong, because this is a very good paper, and obviously winning a research award for the VLDB Best Paper straight away is a good start. So yeah, things are starting well for you. So hopefully the long may that continue for you. So let's speak about that then. So yeah,
I joked at the conference that now it's all downhill, right?
That's
like,
it,
nowhere to go but down.
There'll be a test of time award, surely, right, in 10 years' time as well, Matt. So yeah, we've got that to look forward to at least. Yeah,
hopefully.
But yeah, cool. Yeah, so let's talk about AnyBlox then. So let's first of all, actually, let's give the listener some context on like kind of the domain that we're talking about here a little bit. So this is all about there's a lot of encoding innovations that happen in the research world that very, very, very rarely kind of find their way into industry, into being adopted in practical settings. So why is this? And yeah, just really set the context for us for what we're going to be talking about today and where AnyBlox fits into this whole landscape of computing and encoders and decoders and things.
Yeah, so as I said, if you look at research at SIGBOT, for example, there's a lot of encodings and a lot of new data formats, but in practice, no one uses them. In practice, just everyone uses Parquet, basically. It's like, everything else is like an outlier percentage-wise. Parquet is popular, but it's very hard to extend with those new encodings. This problem is there's this, let's say, semi-famous blog post from DuckDB that they cannot enable like those better encodings for Parquet by default when DuckDB writes data, because there are still some readers out there that don't support it, and you want to be able to support everything, because if there is one thing that you hate as a user, it's dealing with compatibility problems. Anyone who had to manage any kind of dependencies of packages knows that very well. So it's hard to add new stuff. And then if you create a new data format, it's kind of hard to break through, because if you create a new data format and it's supported nowhere, basically, unless you have your own database and you have the support. You have to convince some big system like DuckDB, or I don't know, Spark would be like the main platform for data science, to support your format, and they're not going to do that, because why would they? No one uses it. But of course, no one is going to use it if it's not supported anywhere. So you're in this kind of a loop.
Yeah.
You
Classic
can't really
catch-22,
win.
right? Classic catch-22,
Exactly.
right? So
So Parquet is there, but a lot of people will tell you that it sucks and needs to be updated. People create new file formats, but they're not really used. And there is like a systemic issue here that we kind of identify as an instance of this n times m problem, which is, I know it from compilers, right? It's like this idea that you have n different dialects of a language and then n different architectures or platforms that you want to target. And if you do this naively, you have to do n times m work, because for every language you need a separate compiler for every platform. And that sucks and is unsustainable. And all of those here you have a similar problem where you have n systems, like n different databases, and then you have n different data formats that you would like to support, because nowadays people just put all of their data into a data lake or into a Google Drive, and they are just expect to be able to read it with whatever they want to use. So again, you have this total maintenance and development efforts of n times m, which is not sustainable. So we look at how those problems are solved in compilers. For example, people invented LLVM. I'm not going to take credit for that. So you basically put a layer of abstraction in between. We say that from those languages we create an intermediate thing, and from this intermediate thing we compile to n different targets, and then instead of n times n, you have n plus m. So we are wondering if we can do something similar here, and in particular, like the paper, more than about the product, the end product is like an exploration of what shape should this abstraction have and what are the desired properties of it, so that it works and is nice. Yes, and our answer is AnyBlox. We believe that like our paper substantiates that this is the way to go. Because of course, layers of abstraction introduce overheads, and in the world of databases and like VLDB and Sigmat, we mostly care about performance a lot. So
yeah, that's nice. Yeah, it's a good summary of kind of what the need for AnyBlox, right? And I guess from that, then we should probably talk about. You could maybe give us. I mean, I kind of always like to ask like the sales pitch as well. Like, okay, you've got me in an elevator here, or maybe I'm. I think I would say, what did I write when I see the questions? Like, how would you explain it to your grandma, maybe? But like, so yeah, imagine I have your grandma and like give me like a brief like this is what we do, which is what it is basically, which is what AnyBlox is. I mean, you give a good description there before, but like yeah, concise. Like how would you describe it?
I don't think my grandma knows what Parquet is, so that might be a little hard. But the idea that we bring is that instead of the systems being in charge of how data is read, we should inverse this, and it's the data that should tell you how to read it itself, or as we say, your data should decode itself. Instead of disseminating just name of the
Very
podcast.
nice. Yeah.
So instead of disseminating just your file and some exotic encoding, you also distribute the decoder. And then as long as we have the proper abstraction in place, it should be possible for any system to read this. And AnyBlox basically achieves this. The sales pitch that I would give is like, look, we put some work, and now there's like this the figure in the in the paper, in all of those various systems, Umbra, DuckDB, Spark, Data Fusion, whatever you want, you can read all of those different formats, some of which you never heard of, and you don't need any support from either side, really. Like, you don't have to ask the data system maintainers for permission, and the only thing that you need to understand is how the system works or how the data format works, and that's it.
Nice.
There are, of course, complications, like there's a lot of details hidden in this, but this is the pitch.
That's the core idea. That's very nice. Yeah, it's this, I guess, this idea of self-decoding data, as I think you phrase it in your paper, which is really cool. We're going to talk about some more in some depth. So let's get into the meat of things. And so obviously, the end result was AnyBlox, but there's a journey from going from kind of what was the kind of the state of the art and what people do and how people have solved this, or like what the end times end problem kind of looks like today in the world, to this, getting to this end result. So you approach this in kind of by defining 4 properties that any sort of system like, or thing like AnyBlox would need to satisfy. So yeah, tell us what these 4 properties are, and then we can run through the kind of the approaches and how they compare up against these 4 properties.
Yes. So is the question about what do you want from this abstraction? Like, how do we evaluate, right? Because I'm kind of learning how to properly do research, but the way you're supposed to do science is like, okay, like how do we even test that we got what we wanted, right? So the properties we describe is, first of all, portability. This is like the whole thing, right? Like, we want to be able to use the same solution across all the different systems, and the cost of integrating it shouldn't be too big, right? Because first of all, if we just allow you to do it only on some architectures or only with some kinds of systems, no one's going to use it. If it requires you rewriting your whole database stack, no one's going to use it. So how hard is it to do that? The second thing is security. This is something that an astute listener, when they hear we should distribute code alongside data, immediately thinks is like, what do you want me to just execute random code on my machine, right? So the solution has to be somehow robust for bad decoders, not necessarily even malicious decoders, right? But just bad code. Then performance, again, I think it's self-explanatory, right? You don't want to pay a lot for this abstraction. And finally, this is, I think, the only like non-obvious one, is extensibility, which is like the other side of this end-time sign problem, right? We have portability here for the systems, and for formats, how hard is it to actually make the format conform to the abstraction? Because you could put so many restrictions on what is an appropriate decoder that some of the existing data formats just wouldn't be able to be written into AnyBlox, for example, or it would be extremely hard. You would have to hire a PhD student to do it,
right? Yeah.
Which would also be bad. And then we kind of look at the landscape of what is out there, what are people looking into, and we come into the conclusion that none of the current directions are suitable. They all suffer in at least one of those dimensions, and we need something different.
Nice. Yeah. Let's run through those then. So the first one is the native code approach. So tell us kind of what that actually is, and then why it's bad relative to. I mean, it doesn't perform poorly in all of these measures, right? But on pretty much most of them. So yeah, tell us how it does.
So this is kind of a solution. It's like the baseline that we have, which is how data formats evolve now, which is someone at DuckDB just goes and writes the code that reads, orc, and pushes it to the main branch, and that's it. It just runs natively in the database. As other examples, we use like JSON this is somehow like through like my lifetime, this is like a shift that has happened where people kind of embraced JSON in databases, right? That's when I was starting out, it was like this format in the web, and then people started adding support of it into different databases. Now you can read JSON files basically in anything. So like into Postgres, into MySQL. So this is of course not really an abstraction, but it's a sensible baseline, because for performance, this is the best you can get, right? Because we're assuming that you're taking someone very smart that understands the system in and out, and they can write the most efficient code for that particular decoding, and does the best performance you can get. But of course, this runs straight into the n times n problem. It is not portable nor extensible, because a decoder that you write for one host cannot be really reused in another. For some hosts, of course, this is not even like a possible thing, because for DuckDB, for example, it's at least possible that you can go and propose a change. But if you want to use, I don't know, SQL Server,
no chance, right?
You would have to. Realistically, you have to be like a big corporation that can pay a lot of money to Microsoft to make that feature. For extensibility, it's the same, because I'm looking at it from a user perspective. Like, how hard is it for you as a system developer to implement this into a system, or how hard is it for you as an encoding specialist to develop this as a decoder? And of course, if you wrote, I don't know, better blocks, and you wanted to put it into Postgres without having knowledge of the Postgres code base, it's basically impossible. You have to learn everything. And then the last one is security, for which we actually got a bit of pushback from reviewers, because I marked it as weak. So we have the scale from very weak, average, good, very good. And the pushback was, what do you mean weak? Like, you have an expert developer put code into the database, it gets through pull review and tests, because of course we all have high standards, so there's never going to be any issue with that or any bugs, because we never write bugs, of course. And that's not true. I kind of expected that people might not like this argument, but I put a citation. What I did is I did a little bit of research into this JSON integration that I talked about into like Postgres and various other operating systems, and I just looked at when was this introduced, and then tried to find issues related to JSON and JSON support. There were quite a few, but the one that I cited that was the most worrying was that in Postgres, 5 years later, after introducing support of the JSON type, they had a high severity SVE related to that code that was untouched for 5 years. So my argument here is that you are very much increasing the surface area of possible security bugs by introducing maybe complex decoders. And because there's so many of them, we're talking about like possibly thousands of lines of code. So that's not secure. That's not secure also because it executes at the same privilege level as the rest of the database. So if you're writing a database in C++, something goes wrong with the decoder, you're risking like very serious bugs. And finally, one another thing is that some decoders require external libraries. So the example that I came across is that, for example, if you want to use the roaring bitmap in Rust, the default implementation is just a thin wrapper over a C library that implements roaring, which has some other static dependencies. So we're also increasing the security risk of your whole dependency chain, right? Which, as we know, supply chain attacks are also very hotly contested security battlefields right now. So native suffers from all those shortcomings, and it's kind of a baseline for us. Like, how far can we push? How much better can we get across those three bad dimensions without sacrificing too much of the performance in the process.
Yeah, nice. Essentially, like kind of the security thing about it. I think you say in the paper that it becomes a statistical inevitability in the end, right? And by
Yes.
that. So that's a good way.
Because it's n times m, right? You have just so much code that something is going to go wrong. You might win the lottery and it might not be your system, but
you only have to get unlucky once and then you have a bad time, right? So yeah, it's better to be safe than sorry. Cool. Yeah. So yeah, and you say that another type of approach is extensions. So where do extensions fit into this, and how do they compare up against these 4 principles or pillars of that we want to achieve?
So extensions are a powerful mechanism. It's one of the reasons why DuckDB is so nice and so powerful, is that you can just write your own code and load it as a module and extend the database with something that the developers didn't think about. Now this alleviates some of the issues, mainly extensibility. Like for you as a format author or decoder or encoding author, it's much easier to integrate because you probably just need to wrap your code into the extension API of Postgres or DuckDB, or SQL Server. I think also has an extension mechanism with C# code, and that's it. It works. It's also going to be pretty fast because presumably it is in the same language and also kind of in the same like level of operation. As long as the extensibility API of the system is like sensible and can take advantage of all of the performance features of the system, it's going to be fast. But of course, for portability, it's still bad. You can realistically reuse an extension between 2 systems that are written in the same language, maybe, and have similar APIs. Like the changes probably won't be that big. You still have to maintain both, though.
Yeah.
But the killer here is security, of course, because you are not going to convince someone. Hopefully they are smart enough to refuse. When you send them data and you then send them, a compiled extension and a shared library, and say, just load this into Postgres at the same privilege level as the rest of your database and run this code on your machine. Like that's of course insecure. So that's why it's not going to happen, right? Even for normal users, but of course some like enterprise settings have extremely strict requirements when it comes to code auditing and things like that. So that just is straight up impossible. No one's going to do that.
I guess the next approach then, isolated extensions, is tackling that security aspect a little bit nicer, but that then comes with other trade-offs, right? It trades off some of the other pillars. So yeah, let's give us a quick rundown of isolated extensions, which is the last actual approach people actually do take, right, to this.
Yes. So you can have this idea of having an extension, but instead of putting it into the same assigned domain like in Postgres or DuckDB, where you just load the module, we host it somewhere, I know, on a Docker container, and then whether it runs on localhost or somewhere in the cloud doesn't really matter. And you containerize it, you expose some API for like, here's data to decode, please give me back the tuples, and you run with that. This has very strong security guarantees because it depends on the isolation mechanism you choose, but of course you can run it on a completely separate machine, basically, and then you're in full control of what can happen with that code, what capabilities it has. So security is very strong here. It's also much easier to actually write, because you just need in the examples that I looked at, because this is provided by Snowflake and the AWS the Redshift database. You can host like a Lambda function and have it call into that. It's easier to write because you just get input and you're supposed to produce tuples. Anyone can do that if you already written your decoder. For portability, it's kind of good, like as long as your system supports this approach, right? This framework of decoding, it's quite easy to move, because it's probably just adapting whatever. Usually this happens via HTTP, so whatever REST requests are sent, and it's fine. The minus of this is performance. You are losing the one thing that you're losing is that the code is isolated from the host, so there is an overhead to whatever system you're going to use to call it. Probably some REST, or in the best case, some remote procedure call. But the real killer of performance is data transfer, because you necessarily need to copy all the data into the box, into the isolation layer, and then take the decoded out. And to evaluate how feasible this is, I did a very quick and dirty experiment of like, okay, how I host just a Docker container on the same local host, so there's no network overhead. It just runs some very simple code, try to send data there, and get it back, and the data transfer is immediately the bottleneck.
Right.
The lightweight decoders are very, very fast, so they can decode at multiple gigabytes per second, and the network is not going to, just the data copy is not going to be fast enough. So to alleviate that, you would have to start breaking down barriers somehow, like share the memory somehow, and then you're of course losing the isolation layers. So it's a good approach if you just not for big data, right? If you just care about getting some data and being secure and not really fast, then sure, but this is not why we're here.
Cool, yeah. There's no free lunch, right? There's always trade-offs, right, as well.
Yes.
That's it. So yeah, I guess with that then, so I know there is a another possible approach around static verification, but I'd like to maybe discuss that a little bit later on. I'd like us to get into AnyBlox now. So given what we just spoke about and these 4 pillars, and we want to kind of design something that ticks pretty much all of the boxes, walk us through how AnyBlox does that, walk us through the design and how it works in practice.
So I think an important part of this of the story behind this paper is that the idea of sending code alongside the data is not really a clever idea. Like it doesn't take like an expert to come up with that. You can come up with that yourself. Anyone can come up with that. The problem is that when you start to implement that in practice, suddenly it turns out it's not that easy. Like just saying, "Oh, just distribute code and data." Right? The obvious issue being you're immediately opening up to remote code execution because someone just sends you code that does something bad to your database. There's like a lot of small little design choices that you have to make along the way, and it's not obvious what the correct one is and how it's going to actually impact the 4 properties that we talked about. So naively, to execute some code that decodes the data, you would do something similar to remote to the isolated extensions, right? You would put up some sandbox, copy the data in, run the decoder, copy the data out, and as long as you keep the sandbox like secure, right? You don't give too many capabilities to that environment. That's fine. But those copies are very expensive, as we said.
Yeah.
Most lightweight decoders can decode data faster than memory bandwidth. So avoiding both of those becomes a hard issue. Yes. So in case of WebAssembly, this is what we chose. We looked at other ways of expressing the code. Right. You want it to be portable, so it has to be some language agnostic bytecode or something similar to that. We looked at WebAssembly. For WebAssembly, the good thing is that the sandbox first of all already exists. Like there are WebAssembly runtimes that already exist and do all the things that you would want to do. They isolate, you don't get access to the network, to the file system, to system calls from the isolation layer. So you get kind of security by default by the WebAssembly specification. And then a WebAssembly environment has linear memory, right? That's like the big If you don't know what WebAssembly is, people came up with it to make web browsers faster because they wanted to do more complicated stuff than normal JavaScript would reasonably support with the performance of a scripted interpreted language. So they introduced this WebAssembly that can be JIT compiled to native code and then executed. But of course, we're talking about a browser, so it has to be sandboxed and isolated from the rest of the system. And then, of course, as it usually is with engineers, you give them a toy that's supposed to run in the browser. They take it out of the browser and try to implement all kinds of crazy stuff outside, which is kind of what we did as well. And I'm not saying that it's bad. So to achieve our goals here, we can use the way WebAssembly is usually implemented, which is that you create a memory map that is size of 4 kilobytes, which is as much as you can allocate and address at 32 bits in WebAssembly. And this is a virtual memory map, right? So there's no actual physical memory that's backing it, and you use the usual operating system paging mechanism to say that all of those pages are protected; they cannot be touched. Touching them is a seg fault, and then you have a very easy bump allocator method where when WebAssembly asks you for more memory, you just say, okay, so you want 5 pages. I just tell those 5 pages that now they are read-write. The rest stays the same, and you can avoid all bounds checks because now any access out of bounds immediately runs into your memory protection and you get a seg fault. So this is how most WebAssembly runtimes handle this, including the one that we chose, which was Wasmtime. And the idea that we have is that instead of doing hard copies, we do a trick with memory maps. We call this data hooks, where we say, okay, the database system, whatever the host is that wants to decode some data, gives me a file descriptor. I don't care what exactly this is. This can be a file on disk. This can be a file in memory, like created with memfd. And I memory map it to a fixed spot in this linear memory. This is a very cheap operation. No actual copy happens. This is just telling the operating system to do like a mapping between pages. We said that to be read-only because you don't want the decoder to be able to modify data that is managed by your database. And that's it. We just tell the decoder where it is, and it can access it transparently as if it was copied there. It has no idea that actually underneath this is just like a page. When it accesses it, a page fault happens, and all the usual operating system shenanigans happen to make sure that the data is there. And this completely saves you the copy of on input, right? If you already have the data somewhere in memory, it will just be there. This is just a page mapping. If it's on disk, you have to read it anyway, but it will be only read once. So this was the copy on input, and then the copy on output. There are 2 things here. One thing is that when you say output tuples, what does that mean? As input, you get some well-defined format that you want to decode, but what is the output? Right? Every system has a different internal representation of their tuples. So we chose Apache Arrow as the output format. This is quite natural if you've heard about Arrow. It is also the default format that is already used by some existing database systems like Data Fusion. It's basically a specification of how data is represented in memory, right? So how is a 32-bit integer represented? How is a string represented and laid out for columnar data? So we choose that, and then we say that a key feature of Arrow is that it's 0 copy. This is not a strict term. It's sometimes confusing what it actually means.
Becomes a marketing
but basically,
yeah.
basically it means that if you have an array of integers, for example, in Arrow, and you want to use it from inside your system, you can just use it without copying the entire thing, because it's already laid out like an int32 or i32 in whatever programming language you're using is laid out, as long as you're on the same endianness as the thing that produced the data. Yes, so our decoders produce Apache Arrow, and to avoid copying on output, we say that we want pipelined execution. So this is the way most database systems that care about performance execute stuff, which is they will ask for some batch of tuples. This can be one tuple, but usually it's a little bit more. They take them and then they push them through the pipeline up to a materialization point where something happens. It's put into a hash table. It's copied somewhere anyway. So we say that as long as you use the decoder in this manner, you ask for a batch, you push it to some point, and then you either you use this data somehow or you materialize it explicitly. There will be no copy. The decoder produces it into its linear memory slice, and the host can just access it. So it's fine. The trade-off there is that you cannot rely on the decoder leaving that data alone when it's called to decode another batch. So you have to decode one batch, do something with the data, and you're responsible for. It's basically transient, right? You have to be aware that if you call the decoder again on the same memory map, then the data can go away, be corrupted, whatever can happen to it. So you have to be aware of the lifetime. But again, we implemented this into many different data systems, and in none of them was this a problem, because all of them follow the same principle of pipeline execution. And this saves you the copy on output. This is especially important for string data, where a lot of the decoders are just going to be pointing to data that already exists in the buffer in the input. And you just put a pointer there, and the host just translates the pointer from WASM style offset to its own. And that's it. You don't have to touch the string data. You don't have to copy it at all. So it saves quite a lot of, let's say, a lot of money. I guess time and space is money as well.
Yeah, that's very true. Yeah. Cool. That sounds awesome. So let's talk about evaluation then, and how close AnyBlox actually gets to that sort of theoretical limit, and how well it does on the other stuff as well. So yeah. I guess, is this maybe quite a little bit of a difficult thing to evaluate, like a non-standard thing to evaluate? So how did you actually approach the evaluation? And yeah, what were the key findings?
So we wanted to evaluate it from, we wanted to evaluate all of the properties, of course. The security property kind of evaluates by itself, right? We're not going to claim that WebAssembly is the perfect solution, because of course you are just relying the security guarantee
you inherit it from
to the sandbox.
Yeah.
If the sandbox is broken, your stuff is also broken. But
trade-offs, make some assumptions, right? Yeah. So yeah,
you have to make some assumptions. Yes. But as long as the sandbox is correct and implements the WebAssembly specification, this is also secure, which you can't access, and it's in all dimensions you can think of, because security can also mean that can someone read the data that is supplant, right? Because if you have an extension in your database, there's no guarantee that somewhere in there is not someone that is just sending your data over the wire to themselves, or doing something similar with that, exposing your PII that way. Here, of course, the sandbox doesn't have the network. This is just guaranteed. It's impossible to express a network call in the WebAssembly bytecode, so it's not possible to do. Your memory, your data is secure from the operating system, because it's protected by the memory protection ways of the operating system. So really, the only thing that can happen from the sandbox is that there's a very critical vulnerability, and it accesses something from outside of the memory slice. This is the main vulnerability. Okay, and for the other things, so portability is very important. We implement AnyBlox into a variety of different systems, trying to cover a lot of differences that we can think of. So Umbra and DuckDB were the first ones. Umbra, complicated compiling database, developed at TUM. DuckDB, of course, well known, has a different paradigm. They use vectorized execution, both in C++. Then we implemented it into Spark, which is completely different in Scala. It has like a hybrid execution model because it compiles some expressions, but also uses like vectorized stuff and is highly distributed. And then finally into Data Fusion, which is also vectorized, but uses Arrow natively and also is written in Rust, which AnyBlox is also written in Rust. So we wanted to see how easy it is to do it natively. And there's like this table where I put how much time it took. It's called %days, but it's like to like lift the curtain. That's how long it took me to
It's
implement
Matt days, yeah.
Matt days, yes. And how many lines of code. So the hardest was Umbra, which is not, well, you would expect it was Umbra. Not surprising because again, it's complicated compiled database, and I had no idea. I never saw any of those code bases in my life before I started doing it, and it just took me 10 days. So someone who knew Umbra could probably like put it out in 2. The hardest was Spark, but that's squarely because Spark is just so bad to work with. Like the code doesn't have any documentation, and I don't know, people, Stack Overflow also doesn't know how to implement like custom data sources that do stuff like this. It was just very hard. I had to understand Scala code, which
hard enough yourself, yeah.
I did maybe a tiny bit of Scala programming in college, but that's it. And Data Fusion was just like so we proved that portability works, and then for the other side, for extensibility, to show that we solved the n times n problem, we took various different encodings. So some of them are just raw encodings like run length and FSST directly, just the kernel of the decoder that we implemented. We also took Vortex, which was like the ultimate test, really, which is a full file format written in Rust, very new, very good, very fast. It's really like an alternative to Parquet. And we wanted to see if we can just, compile that into WebAssembly, put it into a decoder, and get away with it. We can. And then another one is Root, which is a very nice compiling story of people at CERN doing high energy physics research. They have their own this custom data format for holding that particle data. It's an insane format that was developed over like a few decades. I don't remember exactly when it was. It was like the 80s or the 90s.
Right.
They developed their own custom data format in C++. It's crazy. Like they have a whole file system abstraction, and they basically reinvented Parquet from first principles.
Okay, cool.
They have a REPL in C++ that you can use to talk to that thing.
Yeah.
It's crazy. And I found a paper where they were looking recently into like, can we just use like normal tools? Like, can we just put our data into BigQuery and ask in SQL something about physics? The answer was that it was not that easy. So we thought it's a very compelling story that here, I have no idea how this format works. I would never know. This was actually done by Maxi. He spent like 2 days just rewriting a subset of Root into Rust, put this into a decoder, and now we can read this high energy physics data. And they were, if you run this through their tools that they use day to day in C++, first of all, you have to write some C++ code yourself, which poor data scientists at CERN. And it doesn't have any parallelism by itself. So you have to do parallelism by yourself in C++. Whereas here, we just put it into Umbra, we write a very simple SQL query, and you get, I think it was like 30 times better performance or something like that, like 6 gigabytes compared to 300 megabytes natively from the root. So there, you can use normal tools now And I think that to me that's like the most compelling story of AnyBlox, that like I have no idea how this file format works. I like barely know how Umbra works, like the basics, right? Here I can use this data with this database system. Just it magically works. It's great.
It's amazing.
And then the rest of the evaluation is, of course, just performance. So for performance, we wanted to focus on analytical workloads first. So how does this work in an actual use case, in an actual system when you run full queries? We look at DuckDB and Spark as two like the most distinct systems that we could. And we choose TPCH, the standard analytical benchmark, and then also ClickBench, because ClickBench has a lot of string data, and we wanted to test like FSST encodings that Vortex uses. And TPCH mostly has numerical stuff. So we do that, and we just check the native system, native DuckDB, how does it do that, versus DuckDB, but using Parquet. Right, so we encode the data into Parquet and then read it using the DuckDB Parquet reader, versus our AnyBlox integration with Vortex. So the story, like the takeaway from this is, despite the fact that we are not native, right, you have this sandboxing.
Yeah.
By using a new cutting edge encoding for your data and the decoder in WebAssembly, you can already outperform native Parquet, both in time and in compression. So Vortex compresses better, and it's much faster to execute even through AnyBlox.
Yeah.
So you can like reap the rewards of the encoding research today without having to go through, the rigmarole of implementing it natively into DuckDB or writing your own extension or anything like that. And that's great. We also show on the charts an important thing that, for example, in TPCH, the Parquet workload spends most of its time decoding data, and then the rest is, useful work of actually running the analytical operators. Whereas for Vortex, it's much better. It's like half of that time. So there's a lot to be gained in those encodings.
For sure. I mean, the whole thing just sounds like a complete win on all fronts, essentially. So that kind of leads me into the sort of next topic I want to talk on, and that is about impact. The first thing is, in the short term, how much impact have you seen AnyBlox have, and has it got any traction beyond the people you've communicated with? I don't know, the people working at on high energy particle physics or anything like that. Like, how is that going? How are we going on that sort of journey of actually making this thing kind of the industry standard / go-to thing for this problem?
So it's quite new. Right? The conference was in September.
Yeah.
Talking there, a lot of people were interested. Like people from Vortex specifically are very interested because they took the story of the paper to mean like, what's the best way to fix Parquet?
Right.
Use AnyBlox to put Vortex into Parquet, and then everything is fixed.
Right. Okay.
Which is of course a very nice story for them.
Yeah.
People from like LANs were also interested in how to use this. I think like it's new, but the potential for the impact is very, very big on like 3 different fronts, I would say. One, for future-proofing file formats. Very shortly after this was published, a very similar work was published in Sigmat, which is called F3, which is something like future file format, something like that. They also use WebAssembly decoders in their thing. The main distinction is that theirs is like a full file format. It's not. Ours is a framework. You can put it into anything. You can put it into your file format. You can use it just raw with some data. You can put it into your data management system. Theirs is like a full file format with a similar idea. So just definitely, it's definitely like a push from our community to get those future-proof file formats. I think the way to have the biggest impact would be to actually get this into Parquet.
Yeah.
This would require, a new version of Parquet, which we already know how adoption goes. But this would mean that Parquet actually becomes extensible and future-proof, right? Because then you can expose any encoding as an AnyBlox encoding. We have an experimental version of that where you basically just... I'm not going to explain how Parquet works, but if you know how Parquet works, you just put a page at the start that is the decoder, and then the rest of the page is like opaque data, and you can use AnyBlox inside the Parquet reader to read through that, and voila, you have your vortex in Parquet. Great.
Yeah.
So that if you get this into Parquet, you get this into every data management system ever at some point. So this would be a very high impact. Another thing that I believe that this can have impact on is like data science. So there's a lot of consumers out there that we probably don't know that well by just going to conferences, which are dominated by enterprise users. But like this high energy physics stuff, I know that people that do bioinformatics have a load of their own different formats, and it would be really nice. Like if, for example, DuckDB, we could release an extension for DuckDB that incorporates AnyBlox, and then data scientists can just do their thing, right? Because from their perspective, the ideal workflow is that they launch a Jupyter notebook, they import DuckDB, and then they download whatever data is given on like a file share that they have, and read it through DuckDB, and they don't care what the format is. They want the data, they want to plot some graph, look at some stuff, and do science. So that would be cool if we allow them to do that. Currently, of course, it's hard. You can't load root into DuckDB, for example. I know that the genomics people have their own issues with databases. So and then the last thing that for like looking forward for the future is that in general, my area of research is this umbrella of future-proof data systems on modern hardware. And the question is like, what does it mean to be future-proof, and then how do you achieve that?
Yeah.
So this is tackling this from like the storage layer. Ideally, you could evolve the storage formats and encodings completely independently of your data systems. If you make AnyBlox the standard that everyone introducing a new file format or a new encoding targets, then any system that already exists that has AnyBlox can read everything. And moreover, if you develop a new system, you don't have to spend time implementing readers. You just implement AnyBlox and you read anything, and you're happy with that. So this is something that I would like to see from systems like LingoDB, for example, which we're also developing at TUM, just looking to be future-proof and open and flexible. Why spend our or like master students' time implementing Parquet into something if we can just do AnyBlox and forget about it? The question of how much impact we will have is basically how much effort is put into this. So the project is open source on GitHub. And it would be it's unfortunately, I have to say that it's research code, right? It's not the highest quality.
I'm sure it's just fine, Matt. Yeah, don't worry about that. You should see some of the code that gets written in enterprise software. So yeah,
I worked at Microsoft. I know. My standards are very high. So for my standards, it's like fine. Okay, but it could be better. It could be packaged better. Needs to be packaged better into like a DuckDB extension. This is something that I'd be looking into doing. But of course, if anyone is interested, it would also be very nice to see people implementing this into different systems and creating encoders into WebAssembly. It's very easy because basically everything compiles to WebAssembly nowadays. As I said, for Vortex, I just took the Rust code base and I just wrote, target wasm something, And then I had to remove like a subdirectory that was dealing with input-output because it was incompatible. But I already complained about this to Vortex people, and I think now their code base just compiles with WebAssembly. That's what they told me. So that's good.
Nice. Yeah.
You get that file, and that's it. You have the decoder. You don't have to do anything because our like this data hook mechanism means that you're just accessing memory transparently. You don't have to worry about anything. You don't know if your decoder is running in AnyBlox or natively. So yeah, like I have big hopes for this project, and I hope we'll manage to get a big impact because the potential and like the community buy-in is there. So just we need to harness that.
Yeah, well, fingers crossed it all turns out. Well, in the interest of time, I'm going to skip over the surprises question. I know we touched on the future one as well, then, just because I actually need to leave the house in about 20 minutes, so I need to we need to wrap things up. Unfortunately, sorry to
I talk too much.
No,
Sorry.
no, it's all great. It's all great stuff. It's good. It's gonna come out fantastic. It's really clear, insightful, and well explained. So it's great stuff. But yeah, with that, let's move on to the last word then. So, what do you want? Firstly, practitioners, people out there in the industry, to take away from this podcast today, and your work on AnyBlox, and also researchers as well. What would you want them to hopefully get from this podcast?
Oh, it's a hard question. Well, it might sound a little rich from me, but I would say that people should stop inventing file formats. Maybe
Yeah.
we have a lot, right? We had Fastlanes come out. We had F3. There was one more that I'm forgetting. Lance, right? And our work is explicitly not a file format. If there is one thing that I want you to take out, is that AnyBlox is not a file format. People already started saying that, and I hate it because very explicitly, this is not a file format. This is like a framework, a method of exposing encodings. We don't care about the physical layout of your data. You can put this into anything. We explicitly require like very little metadata. The only thing that you need to tell us is what the output of the tuple shape is, because obviously, and how many rows there are. And that's all we need to know. You can put this into Parquet. You can embed your own statistics. Right, like that's the other paper from Sigma F3 that I talked about that also uses WebAssembly. You could just replace their mechanism for WebAssembly execution with AnyBlox, and it's fine. Right? We're not a file format. We're much more flexible. Which I think is a big plus because it means that you can actually like push this through. Right? You don't have to fight an uphill battle of everyone now use my file format for stuff. You just have to be like, hey, implement this encoding and you're fine. Yes, so that's like the one thing.
Good message, yeah. You've been told, folks. Remember, AnyBlox is not a file format.
It's not a file format. Yeah, and I think for future research, I think we should, first of all, we should all be a little bit more focused on making stuff open and accessible to other people. Because, this also kind of speaks into impact. On VLDB itself, there was a lot of talk about like, yeah, we do all of this research, but is this actually being used by people? And this is one of those things, right? They're coming up with all those encodings, all those file formats, and then most often your code just remains somewhere on GitHub. It's referenced from a paper, and that's it. No one ever uses it. So we should be like thinking about how we can actually bring those benefits to people. And for example, you have this large community of data scientists that, as the root example and the paper that I cite show, are eager to like use our stuff. For me, it's more idealistic. I would just like to help them and allow them to use our stuff. If you want a more corporate pitch, then like those people want to use BigQuery and give you your money, but we have to allow them to give you money with like making this stuff actually open and accessible. Yes, and for future research for AnyBlox, I think there are a few limitations of this that are like obvious and weren't really addressed, mostly because of time constraints. The major one is filter pushdown. It would be nice if the decoder knew, for example, was able to take some simple filter expressions like eliminate nulls or eliminate this column when it's below 3 or something. Filter pushdown would give a lot. We point out in analysis of experiments like specific queries where we feel that all of the performance that we lose is due to filter pushdown. So there's like low-hanging fruit. The large limitation and like future direction for research that I personally am interested in is WebAssembly is great, but as I said, we're kind of using a tool that's different, that was made for a different purpose, and we're kind of like ham-fisting it here. And it has one big limitation, which is that it can only run in a CPU. You have to like call it as a function, it runs in the sandbox, and it returns, and that's all you get. A lot of people are now looking into both compression and decompression with accelerators or with GPUs, and AnyBlox, in particular WebAssembly, I feel like is not like capable. You can't run WebAssembly on a GPU. Like, you can run it, but you can't have the sandbox. Like the sandbox is very CPU centric and requires CPU facilities. So this is like how far away can you push future proofness?
Yeah.
Right. I like to think that one day someone is going to come up with a chip that we have no idea how it looks like. It's some future processing unit. You don't know what it is. You don't know its architecture.
FPU.
Can we actually design a system that would run on that, even though we don't know how it looks like too much currently? Like how far can you push this abstraction? We have some ideas. They're mostly, ditch WebAssembly and maybe talk about decoders on a more abstract level. Maybe we need a specific dialect, like a DSL or something that then would be compiled. I feel like there's a lot of good research that could be done there, especially now that there is a push for like, as I said, GPU and accelerators, heterogeneous hardware and stuff like that. So I think that's it.
Cool. That's a great message to end on there, Matt. Thank you very much for taking the time to talk with us today. It's been a very, very insightful chat. I'm sure the listener will really have enjoyed it. Best of luck with the rest of your PhD and the rest of your academic career as well. We'll be keeping an eye on you for sure. I'm sure there's plenty of good research to come.
Yeah. I'll see you on the next Best Paper Award.
Exactly. There we go. That's it. I expect one every time now, Matt. That's it. Yeah.
Oh no.
Cool. We'll end things there.